We're going to do section 14.4, tangent planes. And to find a tangent plane, we need a formula. And to get that formula, we're going to have to use the equation of a plane passing through point.
It's the word plane.
Oh,
I know you got it for me.
equation. Wait, I did that right. Passing through a point, and we're going to call that point P with x naught, y naught, z naught. And that equation is given by A times x minus x naught plus B times y minus y naught plus C times z minus c naught, all equal to 0. And to get this equation, what we're going to do is we're going to move this term over to the other side. So that's going to leave us with a x minus x naught plus b y minus y naught equals minus c minus c naught. Now what we're going to do is we want to eliminate these terms and kind of change them around. So we're going to divide the equation by a negative c, and then we're going to assign some variables to our components. So when we divide through, we're left with and I'm going to do it like this. Now we're going to do a variable substitution here, and we're going to let little a equal part negative a over c, and likewise we're going to let little b equal negative b over c. So substituting that in, our new equation is going to look like this, plus little b. All right, now that we have that, what we need to do is we need to hold our y naught term and our x naught term constant, and I'll draw a graph after I get done deriving the equation, and it'll make more sense. But we're going to hold those two things constant, substitute it in, and we're going to get the equation which looks like this. So for y equal to y naught, we substitute it in, and we get z minus c naught. And here's where I did my substitution. Now evaluating this is going to go to 0, so that b term is going to go away, and we're going to be left with z minus z naught is equal to a x minus x naught. So now we have a kind of a line that's going to be tangent to a point on our plane. And we're going to do the same thing holding x naught constant, and I'm just going to write the answer. I'm going to skip down here. So for x equal to x naught, it's going to give us okay. Now that we have those two equations, we're going to call these point slope equations, because that's basically what they are. Very similar to that, we have the slope and the two equations, or the point and which leads to the equation. So we have a slope, and I'm kind of skipping around here, but it'll make more sense in a minute when I draw the example. We're going to say we have an equation in point-slope form. With a slope of little a and little b, respectively, to those two equations. Okay, now that we know slope, we know that the slope is equal, we're going to call this one tangent 1 for the holding the y constant to y naught. And we know that that slope is going to be equal to the partial derivative of x for x and y. And likewise, the tangent slope for 2. Yes, sir.
You mean the slope of T1?
The slope of T1 is...
Or either that or T1 is, because it looks like A and B are the slopes.
A and B is the slope, but T1 is the line tangent with the slope. T1 is the line tangent with the slope of the partial derivative. Yes. You want me to write that?
Yeah, because right now we work
Yeah.
T1 is the slope
Yeah.
of T1.
All right, let me make that correction. So T1 is the line where the slope is the partial derivative of x and y. So what that's saying is, to find, we're going to have a surface, and I'm going to go ahead and draw it so it kind of makes sense down here. So we have our graph. And we have our generic surface S. And we have a point on the surface, and that point is our P, x naught, y naught, z naught. And then what we're doing by holding the x naught and y naught constant, what we're doing is we're creating two intersecting curves at that point. So we have a curve that kind of follows that path, and we'll just call that C1. And we have a curve that follows that path. We'll call that C2. And then from those curves, we find a tangent line to those, and two lines make a plane. And that's where we get the equation for our tangent plane. So what we've done is we've created a tangent line to curve 1 that kind of goes like that, and we'll call that T1. And then we have another one going through like that, and we'll call that T2. And that's where I'm getting that T1, T2. And then that leads us to a plane that's tangent to our surface S. But see, that's what we made them. What we did is we took this curve, this dotted line, and what we've done by holding x naught and y naught constant, we've made it parallel to that plane of the origin of y and x. And by holding those things parallel for the x and the y, that's where we get those tangent lines to it.
But to answer Roberto's question, they don't have to. There are infinitely many tangents through the surface on that particular plane. But in order to create that, and that's what that did, we chose these two particular tangents. One is the tangent to the curve, C1. What is C1? C1 is really the intersection of a vertical plane, x equals x sub 0, with the surface and another vertical plane, y equals y sub 0. And that created C2. So now he's taking, okay, one line will be the tangent to one curve, the other the tangent to the other curve. Now we have two tangents. That's sufficient to come up with the relation. But there are infinitely many other tangents to these points.
So these two lines then, they're what we found the equation to over here with P.
Which two lines?
C1 and C.
C1 or T1?
C1 and C2.
C1 and C2. Okay, so this surface right here is just a generic surface S. Okay? Now what we did is we projected a plane parallel to X and parallel to Y, and the intersection of that plane we projected to our surface S created that curve C1.
Okay. Okay, so what are the lines that are just sitting on top of it? It looks like an envelope.
This line right here?
Yeah, that line.
This line right here, that's our tangent line to curve C1.
And these are really equal to the curve here.
What we found the partial derivative is the slope of the tangent line T1.
Okay. Okay.
Okay, so f of x is just the slope to the tangent point P on C1. All right, so T2 slope is going to be equal to the partial derivative with respect to y of xy, which that leads us to just a substitution, which we can say A is going to equal the partial derivative f of x, xy, and B is going to equal f with respect to y, xy. All right? So knowing that, we have to make one assumption, and the assumption is we assuming that f has a continuous partial derivative so assuming that, we can say that the equation for a tangent plane to a surface is going to be given by this equation.
I mean, I can retire.
All right.
I can retire someday.
All right, so that's the equation we really needed. So we went through all that just to get this equation. And this looks very similar to just any standard equation for a tangent line, which was y minus y naught equals f of x, which would be the slope times x minus x naught. So that's a quick way to memorize this formula. Okay, so all that being said, now we can do the example very quickly. Did anybody need this equation still? All right, so the example is going to be book example number 5, and we're going to want to find an equation of the tangent plane to the equation z equals y cosine x minus y at the point 2, 2, 2. So the way we're going to find this is we're going to set z equal to, z is going to be equal to our function f of y, which is equal to the given equation y cosine x minus y. And what we're going to do is we're going to evaluate the partial derivative with respect to x and respect to y, and evaluate it at the given point. So f, the partial derivative with respect to x, y, is equal to, and I'm going to go ahead and do this in my head, and we are going to get y times negative sine of x. So all I did was the chain rule here to solve this, holding y constant, the inside times the derivative of the y's, everybody knows that, which then reduces to negative y sine x minus y. Okay, now we're going to evaluate the partial derivative at point 2, and we're going to get negative 2 sine of 0, because 2 minus 2 is 0, which leads to a solution of 0. Is there a question? Okay. Now we're going to do the same thing for the partial derivative with respect to y, and we get f with respect to y of x comma y. It's going to equal, and we're going to have to do the product rule and a little chain rule here. And it's going to look like sine y sine of x minus y times the negative 1 derivative of the inside, and then we're going to be plus. Then the second part is cosine x minus y times 1, which is going to reduce to y sine x minus y plus cosine x minus y. All right, now we're going to evaluate at our point 2, so equals 1. Sine of 0 is 0, so that term goes away. Cosine of 0 is 1, so that is all we're left with. Now we just substitute our found values along with our point into our equation here, solve, and we have the equation of the tangent line. So that's going to... Tangent plane, thank you. All right, I'm going to slide this like this, so everybody can still see the formula. I'm going to rewrite our formula we're substituting in. Now I'm going to substitute in my values. My term was 0. Minus 2 plus 1 y minus 2. And then evaluating, that term's going to go away. That's going to be a negative 2, so we're going to be left with z equals 5. There's the solution.
All right, so